Hello, everyone. This is Minu. I was a research intern at MERL over the last summer. Today, I will be sharing about our work in exploring the neural network architectures for the optimal facilitation of the inverse design of nanophotonic devices. The neural networks has been widely used for the photonic device design application. For example, this work, they targeted to design a power splitter in the silicon on insulator platform for a broadband device. And the design area consists of 20 by 20 grid. They have choice to fill the space with silicon or silicon dioxide. So basically the design space is 2 to the 400th choice. And then by training the network with well-defined training data set, they were able to feed the desired device performance into the network and get the desired device design that achieves certain performance. And in a similar way, the same kind of a work was also done in these kind of a meta surfaces where they care the far field reflection for certain polarization modes. And these works were extended to the uses of generative models. And the advantage of these generative models is that by the usage of this latent variable, for a given device desired performance, the network can output more than one device design. So it's not one-to-one mapping, but by the help of latent variable, it outputs multiple device design with slightly different nuances. So, and we're hoping that some of them works better than the other. So basically by exploring the latent space, we can push the device performance further. And similar concept was also done in the context of the integrated photonics devices. The last piece of work I have to introduce before going to my work is in the field of neural network, this concept of auto Bayes has been recently introduced. You want to search for the right and optimal Bayesian or inference network architecture that assumes certain statistical dependency model among the system variables. And depending which model you choose to use, it's going to determine the network architecture for the problem. And based on certain properties of the problem, you have to choose the right design. For example, in this case, you can choose whether to have or not this latent variable or nuances variable. And depending on the problem specifics, the optimal design can differ. So we want to explore whether this kind of a auto-based approach can be useful even for the photonic device design. The system we consider is integrated photonic platform for wavelength de-multiplexer. And we combine that with liquid crystal to add more complexity by having this tunable material. So here we consider silicon nitride on insulator platform. So this black area is the silicon nitride, and the whole device is immersed into this liquid crystal. And by changing the voltage that is applied across the liquid crystal, the device can perform in a different mode. Basically, the targeted performance is, let's say for liquid crystal molecules are pointing parallel to the this device plane. In that case, you can see that at a λ1 wavelength window, the port 1 is on and port 2 is off, and vice versa for λ2. But then this on and off relationship is flipped for liquid crystal off mode. So we want to basically achieve this liquid crystal tuned switchable wavelength demultiplexer device. And out of this device, we can come up with these different statistical dependency model. Here, S prime is the user-friendly spectrum information, so that cares only about the specific wavelength window that matters for the actual spec, the actual extinction ratio that determines the performance of the device. So lambda bar is the average of two wavelength windows. Delta lambda is their difference. Extinction ratio is the average of these four extinction ratios. And S is the full spectrum. In principle, we don't need the information about what's going on outside of these wavelength windows, but what if we take this information into account when we design the network? And T is the device topology. And we can choose to use the latent variable or not. And for example, in this case, when we choose to work with the network architecture where the full spectrum is inferred by the user-friendly information plus a certain latent variable, and in turn, the topology, device topology is inferred by the full spectrum plus latent variable. So in this case, it requires the network to be designed in this way. It consists of two pairs of encoder-decoder. In details, it will manifest in this kind of network architecture where all the blue blocks are the fully connected layers, oranges are the convolution layers, and the greens are the deconvolution layers. Here, the red boxes are the adversarial blocks. So what this is, it ensures that these latent variables doesn't contain the information that overlaps with the information that the actual system variable entails. So we penalize whenever the latent variable starts to carry out actual physical information. We train the network using these loss conditions. And then we train the network using a specifically designed data set. We optimize this device topology starting from this specific wavelength conditions using this adjoint method. And then we take the end result from this point and use it as initial condition for the optimization of nearby adjacent wavelength conditions. And we cascade it so that it ensures the continuity among these data sets so that the network can do some meaningful interpolation work. So this is the result of the network validation. And so this was the training data set, and then the three different networks were trained. Then we asked each of them to generate a useful device design targeting these wavelength specs and a certain extinction ratio. And this is the result of the generated devices. So each devices were computed, each topology design was computed using FDTD simulation. And then we found the optimal wavelength window condition for each device. And we plotted the extinction ratio in the color plot. And you can see that overall, in terms of the extinction ratio, the most complicated network design that makes use of the full spectrum information, it's best in terms of extinction ratio, whereas it performs quite poorly in terms of covering the wavelength spec conditions in uniformly. So it features this clustering that we don't want in principle. As a side note, it takes about a day or two to run the adjoint method for each of these points. And once we complete this training data set, it takes about 1 or 2 hours to train each of the network. And it takes about only 2 to 3 minutes to generate a device topology and validate it in FTTD. So if you're targeting to generate a bunch of different target wavelength spec devices, this method can win some time for you. So yeah, as I mentioned, of course, we need more validations, but at least for now, with our data, we can conclude that the inclusion of the full spectrum information, it helps in terms of better generated extinction ratio values, but it seems for uniform interpolation in the wavelength spec parameter space, it's better to use these simpler, user-friendly, intuitive information. So as a conclusion, we have demonstrated this auto-based type of exploration of network architecture to optimize the deep neural network for a complex photonic system inverse design process. And we have shown that different architectures comes with different advantages, especially in the context of narrowband performing devices. The usage of the full spectrum, which means the information that happens outside of the wavelength windows that actually matter for the device spec, it comes with both plus and minus. And for the future direction, it might be beneficial to make use of the power of generative model using certain latent space optimization algorithms. So with that, I would like to conclude my talk, and I'll be glad to take any questions from the audience. Thank you for your attention.